Anyway, I think that's all I want to say about that. It's extra credit, so you can do it if you want to. It's not horrific, but the reason I'm okay with leaving it is because they don't even show you the whole picture anyway, which always irks me. And for me to show you the entire picture is going to push us way back. And Laplace transforms are much more important than the 6-3, to be honest, just to be blunt. Hopefully 6-3 is okay with that.
I feel like I've done this in physics too for some reason.
Laplace transform?
Yes.
Yeah. Oh, yeah.
Okay, then yeah.
Yeah.
Sounds familiar.
Yeah. There, I think I can't remember now if I said this in here, but integral transforms. In fact, transforms. If I just say the word transform, some of us go immediately to Optimus Prime and roll out. But mathematically, transforms. What do you think?
Sliding.
Yes. Sliding. You can transform it left and right. Just like we're transforming the n, we're moving it, right? Transform is a more general term, like translation is a type of transformation. Reflection is a type of transformation. I like it. The idea of transforms is even more general than that. It's I could transform a problem into its geometric equivalent, work it out geometrically, and then bring it back. And that would be a transform. I transform the problem into a different system somehow, because it's easier to work with, and then I transform it back. So a very, very simple example of that is U-sub, or trig sub. Those are transforms. And by using those, I make the thing I'm working with look better, I work it out, and then at the end, I better freaking bring it back. From theta back to x, right? So we know transforms already. We just have never, I don't think at this point you've seen the idea of an integral transform. And if you search integral transform on Google, you can find lists, just long-ass lists of these things. And you see these people's names like Weierstrass and Mellon and all these different names of people. And you're like, oh, these poor people. I never heard of these people. They did a lot of shit, and they're dead. Oh, well. And I don't know them. I don't know their stuff. But now you do. Eh? You can go look at it. So, somebody brought up like Fourier series transforms. It's got the word transform in it, so that's kind of a giveaway. So what the hell is Laplace transforms all about? Oops.
This is 7-1.
Oh, this is the thing I didn't... This is 7-1, yeah. So the general idea of a transform, of an integral transform, they have this on the first page here. Let me make sure I get this the same way. So it's this is the function that I'm given, that I'm working with. Sort of like I give you the integral of, square root of 1 minus x squared dx. So I'm given that function, and then I can transform it. So here, the integral transform involves, now this looks like there's not much promise here for this to make this easier, but that's just because we don't know what this really comes out to be. This is, for any integral transform, it's really built on what this thing is, and this is called the kernel function. Function of possibly up to 2 variables. So for integral transforms, that kernel is what changes between all of them. Yes?
Is that a T or an X?
T. These are all T. T. S and T, yeah, sorry. I remember S and T are, T especially is the parameter kind of variable. It's our go-to variable to make it something other than X.
So what does a kernel do exactly? It just transforms it to what form?
That is sort of like, so if I had this, what would you use to do this? Can you use U-sub?
Well, that's
Yeah.
just kidding.
How would you use trig sub?
Isn't trig
Like
sub?
u equal 1 minus, oh, my bad.
There you go. All right, cool.
That's trig sub.
Trig sub.
Sine.
So what would you
Sine
use?
is a cosine, so, yeah. X squared, x equals to sine.
Sine,
Yeah.
because what trig identities is look like 1 minus sine squared is cosine squared. So what would you use if it was this? X equals tangent, because 1 plus tangent squared equals secant squared. So dependent on the function you're working with, or this isn't exactly related to this, but it's sort of analogous, I change the transform I use. So if it was minus, I use x equals sine theta. If it was plus, I use x equals tangent theta. If it was turned around, I would use x equals secant theta. Right? This kernel is sort of the same idea, except it's a little more broad than that. It depends on what type of transform. So the type of transform determines what this kernel is. So for Laplace transforms, the kernel is e to the negative st. I know right now you have very little faith that this somehow makes anything easier. Right? I don't blame you. I was the same way when I first saw them. Like, that just looks like you're convoluting everything. But you don't even know yet what this thing does to derivatives. And those are so beautiful. And why would I care what this thing does to derivatives? Because we're in freaking differential equations. So what does this thing do to a DE? Does it change it into something easier to work with? Yes. Yes, it does. It's crazy. Let's try a couple of things, and then I'm going to let us out a little bit earlier. What if f of t equals 1? Take a minute and figure out what that becomes. Now, what is your variable?
S.
For the integral, your variable is t. That's what I meant. So you're good point. And then the resultant function is going to be all about s, right? Because this t is being evaluated from 0 to infinity. You know, you could do the limit as b goes to infinity with a b there, blah, blah, who cares? I'm only a big fan of completely perfect notation if you are submitting a paper to some mathematical society. You have to have your own notation that works for you until you have to actually submit it to somebody. I don't care, you guys. We know it's going to be a limit. We know we can't plug infinity in. In fact, there was one, I can't remember what, I said, put a BFN in there, big freaking number, right? Instead, because I kept having everybody putting infinity into stuff. Infinity squared. I'm like, no, that means shit. So put big freaking number squared, and that comes out to be a big freaking number. Okay, so that limit is infinity. Oh, okay. Anyway, sorry. So that's just trying to make sure that you don't try to plug infinity in, because that's a no-no. You can't do that. That means you can get to infinity, pick it up, and put it somewhere, and you got to let me know if you're able to do that.
Negative S e to t. I mean, e to st.
Yeah, the interval is going to be itself
Divided by
divided by
st.
Just s. Negative s.
negative s. Because if you try to differentiate this, it'll be itself times negative s. So the integral better divide by it, so that shit ain't there, because it ain't there. Yes, sir?
Is S a constant?
No, s is going to be our variable for, it's sort of like when I do trig sub, the given variable is x, and then the substitution variable is theta. The given variable is t, the resultant variable in the transformation is going to be s. So watch what happens here. This is going to be from 0 to infinity. And again, if you really need to limit, and there's a b, whatever. When I plug infinity in, when I let t get really big, this, of course, goes to 0, because it's 1 over e to the really big, right? So that's 0 minus. When I plug a 0 in, I get 1 over negative s. So I get 1 over s. So the Laplace transform, which we use this symbol for the Laplace transform, ooh, it's a nice big L, of 1 is 1 over s. Our first official Laplace transform. So now you can start to say, okay, that's what it does to a constant function. So of course, what's the Laplace transform of 3?
3 over s.
3 over s. Because the 3 would just come out of the integral and it would just multiply the result. Right? So the Laplace transform of A
I over s.
is A over s. Yes, sir?
And then the thing getting Laplaced is what your f of t is?
Yes, exactly.
Okay.
Right, so that's the thing I'm going to put in here. So then I can say, well, what would the Laplace of x be? Well, or in this case, I'm sorry, Laplace of, in terms of t, Laplace of t be? What would the Laplacian of t be? And I think officially it's this. For this book, anyway. Yes, okay. What would it do? Well, then you just plug a t into here, and then what would that involve?
By part.
By parts, but you can still do it. You can start to see what do these functions become as the transformed look. And you still don't fully buy in, and I don't blame you, that this makes something easier. But we're just starting, right? The next step is to just create a list of original f of t functions and what they look like once they've been transformed. And then we can start to look at derivatives. What happens when I plug a derivative f prime of t in here? What happens to that? And then I can start doing stuff, Laplace transform an entire dE. And see what it does. So I would Laplace transform it, solve it in terms of s, and then inverse Laplace it back. So there's going to be a whole list of inverse Laplace. So what would the inverse Laplace of 2 over s be?
S over
2.
2. Because Laplace of 2 would be 2 over s, right? Okay, all right. I think that's plenty. That's plenty. So we took a baby step into section 7.1. 6.3 is extra credit.
That was a baby step?
That was a baby step.
Oh, wow.
Big time.
I feel like it's not a marathon.
No. This is all we did in chapter 7. This is it. Right? I think the other stuff kind of contributes a
That was
little
a
bit.
marathon.
Really? Damn.